So earlier we had a longer stream. I'll link it down below, but it had to do with figuring out where we're at with quantum gravity. Now we're starting with a question, and this question involves all the relative forces that would be involved in a black hole. Because when it comes to figuring out quantum gravity, one way that we can try to figure it out, besides looking at the entire universe, the space of the universe, and the acceleration of the expansion of space of the universe, we can also look at where the force itself might be derived from in terms of everything involved with the existence of a black hole, as a black hole being essentially the personification of extinction, where the whole information paradox exists, where there's no real way to trace the source of the particles and the matter which they came from before they entered the black hole, right? That's at least the paradox that exists. Is there's no way to understand what information is in there between, I mean, one, we can't observe within the singularity. It's just not physically possible. And two, there's a lot of questions, and there's a lot of things to take into account to try to figure out where quantum gravity is within the whole idea of a black hole. And we run this question through Google. We had a few iterations. We went over it in a longer stream, but to start off, since thermodynamics plays a role with the singularity density of a black hole tending toward infinity due to the effects of a vacuum energy and vacuum pressure, the effects on the Higgs field surrounding the singularity as it rotates near the speed of light, being fueled by the forces from the reaction spontaneously occurring within and around the singularity, while the rotational forces from the singularity as it rotates near the speed of light, which causes frame lagging or frame dragging around it, which maintains the gravitational pull of the event horizon while mitigating the effects of the forces of electron capture interactions due to the density from the sum of frame dragging force and gravitational pull, while matter being attracted toward the singularity due to magnetic forces, the frame dragging mentioned from the rotational force of the singularity, which overpowers the beta decay rates, and the repulsion force from the strong nuclear force of what's within the singularity being suppressed by the forces responsible for maintaining the density and pressure towards the center of the black hole, while the forces from annihilation of particle and antiparticles within the singularity and event horizon, which creates various other particles, and the neutrino and radiation evaporation between the event horizon relative to, well, between at the whatever at the event horizon relative to the total particle mass and the volume of the singularity as the sum of the forces relative to the rotational mass of the singularity, which overwhelms the neutron density limit within the singularity. Code an equation, yada yada yada. Jesus Christ. I don't know why the friggin' AI was having trouble. So, to list off at least what's being mentioned, at least in my mind, theoretically, frame dragging certainly has to do with gravity in some sense, which is the rotational, like the torsion of space-time itself. All right? And the torsion of, I mean, if you're twisting space-time, then whatever is within that space-time is also going to be twisted. It's also, there's going to be a force applied to it in some way, shape, or form. You can think of like how springs work, how Newtonian physics in that essence, because of that effect. So I ran at least the imperfect version of this question through Google, and at least we finally, after a few iterations of the question and trying to also include the Higgs field from our previous statement, going over everything, because it's a lot. And by the end of it, we summarize that the query synthesizes many advanced concepts related to black holes and physics at the most extreme scales. But it is not possible to combine them into a single equation for quantum gravity. Which, yeah, I mean, if there was, then we would have already had it, obviously. But the point being that what was mentioned within that question, the tendency of infinite density toward the singularity. All right. The singularity where mass is compressed to a point of zero volume and infinite density is a prediction of classical general relativity. I mean, not a physically expected reality. The infinity simply indicates general relativity breaks down at this point, which is true, but at the same time, this is a tendency towards infinity. It doesn't mean that is equal to infinity, right? It's all the forces, all those collective forces, due to the frame dragging, due to the amount of mass within that area, and the electromagnetic connections between the particles, the atoms within that area that are all trying to react, right? That are so dense in that activity to a point where it's overwhelming all the other laws of physics, essentially. To a point that it's bending space-time itself. Is just that dense. It breaks. There's a mechanism that breaks the measurement of mass, which is relative to the Higgs field, because the Higgs field is the energy field that is weighed against when, I mean, the Higgs boson turns into other particles and stuff like that, but that is what gives mass to all the other particles, basically. And then collectively, that mass is, what we measure today, relativistically, whether it's, on Earth with Earth's gravitational pull, that rotation of the mass, as well as the physical mass itself existing, because you can have additional force from this frame dragging, but it's somewhat negligible. But when it comes to gravity in the Newtonian sense, but I mean, he figured out with the ratio, using ratios and stuff, what the gravitational constant was between two masses, and was able to figure out through that perspective at least a general equation that works in our 3D space. So that's why that equation does not work in the quantum realm, because we're dealing with wave functions. So exploring these limits, exploring all these different forces that are involved, what it does exist with the black hole and what does not exist anymore in terms of like electron degeneracy, beta decay, like those things, those certain interactions and actions. Because if we can single out what interactions exist within a singularity, then we can figure out what's going on in the singularity, because we know what's coming out. By the end of the day, it's Hawking radiation and neutrinos. We know what's being evaporated out. We know the output. We know what it looks like. We know what's around it. We know the speed at which it's rotating. We know a multitude of different forces associated with a black hole. And with that, we can, as well as the whole idea of tending toward infinite density, tending towards zero volume, when, I mean, as we observe, there's not zero volume. There is a volume. It's more so the mass itself is not relative to the mass that exists out in space, in the vacuum of space. That's another factor too, as well as vacuum energy, which cosmological coupling. It's a very interesting observation that black holes might absorb vacuum energy, which is due to the vacuum pressure between two different objects in space, because that's part of the gravitational force, I believe, at least, that is involved. So with that in mind, with the fact that the vacuum of space itself has a pressure, it has an energy, and if the singularity itself is warping space-time, fighting against the fabric of space itself, essentially, that vacuum energy and vacuum pressure is inherently acting upon it, but it's not, I mean, it's being overwhelmed by the severe amount of density due to the severe amount of gravity that exists because of the mass density being tending toward infinity. So, with that, as well as understanding the Higgs field and what happens with that, because that is a part of space, right? It is a layer of space, and it also has a tendency at extreme temperatures, which, I mean, density is relative to temperature. It's relative to the laws of thermodynamics. Those still exist. There is a temperature of the black hole that's observed, and it's inverse to the mass of the black hole. As in, the bigger the black hole, the colder it's going to be on the outside as we observe it, as we measure it, because we're measuring the outside of it. We're not measuring internally. Whereas, obviously, internally it's going toward infinite density, especially at the very center of that singularity, very center point, as everything collapses toward that center because of the gravitational pull or just the interactions that exist within it. And this is going to go into something else that I just learned about a little bit, but also is very interesting. But the fact that the smaller a black hole is, less mass, the higher temperature it is, and they can get very hot when they're smaller. So this alludes to, the observation of temperature through that mass relative to the tendency toward infinite density at the center of the singularity, because as it gets smaller, we get closer to the center of the singularity, right? And then it gets smaller, it's hotter, it evaporates faster, it speeds up. So there is something there that is a force that's existing. It's that is happening because of quantum gravity itself, because of the sum of the quantum gravitational forces between particles within the singularity that exist. Now, this will end up going into the Bose-Einstein condensate, which is something that I just learned about because apparently a 15-year-old in Norway or Germany or wherever just got a PhD on it. So I was like, what? But looking at that and understanding the state of the singularity itself as relative to the evolution from a neutron star, depending on, the critical mass, to a quark cloud, to a black hole, where a neutron star is like a superfluid. It's measured as a superfluid. And then a quark cloud it's a cloud. It's gas. It's very compact gas. There's a lot of different forces, but then when we get to a black hole, it's a whole different state of matter that just doesn't exist in our 3D reality. But as when I looked into the Bose-Einstein condensate, the consistency seems to be very relativistic to the singularity of a black hole in a super solid, basically. And then you get the whole idea of dark matter, and then the analogies or the analogs that are relative to the Bose-Einstein condensate, which is also relative to thermodynamics, because it has to do with when you approach toward absolute zero, which is inversely to the center of the singularity. Because again, like we just discussed, as a black hole evaporates, it shrinks. When less mass, it's hotter toward the center. It's observably hotter, and things happen quicker, right? There's not as much density anymore. There's not as much forces. There's not as much mass that can contribute to that gravitational force within that point in space-time. So more stuff is allowed to happen because it's theoretically there's more, well, not more space around it. There's actually less surface area. So that's where a lot of inverses come into play, and this is where things get very confusing. But to at least establish where we are at, we need to acknowledge all these forces and at least know what is involved and what isn't involved and what could actually be quantum gravity. And also understanding where inverses come into play, where integrals come into play, because when we're talking about the tendency toward infinite density, we're also talking about the tendency inversely to zero volume. All right? And that way of looking at everything in regards to mass, volume, and density relative to objects in space and reality and everything else, there's measurable volume, there's an observable volume that is clearly much different than the theoretical density, right? Even though there's also like a mass density that is followed, that is understood about black holes. So something is broken there. And personally, I think it's the idea that mass even exists anymore, essentially, or is in a state of non-existence. It is in interaction. It is busy. It is breaking down into, the fundamental particles that we see evaporate from a black hole, as well as anti-particle and particle annihilation, because there's so many interactions that are breaking things down past the point of beta decay, past the strong nuclear force, past the weak nuclear force when it comes to the quantum. Like, those aspects of the equation just don't work anymore, and that's where we get into the Bose-Einstein condensates. So, and that's relative to the Higgs field somewhere. Now, that black hole vacuum decay and other theories suggest that primordial black holes could trigger the decay of the Higgs vacuum, leading to a catastrophic end of the universe. But, I mean, the fact that this hasn't happened yet doesn't make sense, right? And I think one way to look at it, too, is, I mean, the vacuum of space itself is so massive that, I mean, matter itself is, or, well, or dark matter, I mean, as well, but it makes up a majority of space, right? I mean, space also, like, antimatter and stuff like that, it's not easily observed. It's now just becoming observable through, you know, these different mechanisms of measurement. But in regards to, like, our chirality, our existence in the universe, there's obviously a bias. And that bias is that, I mean, existence happens over time, and that goes back to our philosophical theory of everything that we have, is like a model of basically just putting everything together in simple terms. So then we get to frame dragon and gravitational forces. Frame dragon, as you noted, a rotating black hole drags space-time with it. I mean, it's rotating near the speed of light. This effect, predicted by general relativity, so this is supported by general relativity, is enormous near a black hole. It influences the motion of matter, including its orbital dynamics and formation of jets in the, what happens in the event horizon. And then gravitational dominance. While the strong nuclear force is powerful at extremely short distances, gravity accumulates over mass. This is where the Higgs field is broken. This is why we have the pure blackness of a singularity, and why it looks the way it looks, why it's somewhat anchored, but it's not really. I mean, they do interact with other black holes, as we've seen with, black holes combining with other ones, and then the gravitational waves that come from that cumulative gravitational force from the combination of mass, but also the interactions kind of being spread into that point of space. It's interesting. And then particle interactions inside the black hole, so electron capture and beta decay inside a collapsing star. This is like the threshold that we're mentioning, because this is the point where gravity overpowers these two real conditions of particles, right? It overpowers the fundamental way that particles work in space and in reality. So inside a collapsing star, electrons are forced into protons to form neutrons through electron capture, a process that continues until it's prevented by neutron degeneracy pressure. However, if gravity is strong enough, as in the formation of a black hole, it overwhelms this degeneracy pressure. So that's interesting. It's as though electron capture prevails in essence, and this might be why we observe radiation and photon, Hawking radiation, as well as neutrinos coming from black holes, because those are the only particles that can probably make it through that density. As, I mean, it's not a neutron star, it's past that point, it's past that critical mass. So understanding what effects exist and what do not within the singularity, by observing what happens through its evaporation over time, we can start getting somewhere with this. And I mean, I'm sure there's other people that say things like this or have had these ideas, but if we actually did understand how quantum gravity works and where it lies, especially within a black hole, is that something that we can measure and observe, because it's easier to do that than to measure the acceleration of the expansion of the universe. Because at one time you have to be able to account for every star in the position at the exact point of time, and you have to account for the time dilation, not even just the time dilation, but the time lag from observation of stars in the distance, because it takes time for light to reach us. When we observe stars that are hundreds of light years away, that's hundreds of light years in the past, or, well, 100 years in the past, basically. It's 100 light years away. So, I mean, if it's a million light years away, but is strong enough to shine bright enough to get to us, that's a million years ago. And that kind of matters in the grand scheme of things, especially with if it exists anymore or not, because a million years, depending on the locality of what we're observing, it could have interacted with the black hole, it could have interacted with another star, it could have evolved, it could have been within the life stage or whatever. And it's to account for all of that within the universe at the same time and to get an accurate picture of the universe now and then to do it again after a certain period of time to get again an accurate picture of the entire universe that we can observe and then to figure out the expansion through that's a much harder way to figure this out because then you have to do a bunch of points, measure the expansion from one object to another. We can do it locally, but that still doesn't give us quantum gravity. That's how we got Newtonian gravity. We'd have to do it in regards to the entire universe as the sum of quantum gravitation or the quantum particles that are being shed into the universe to make up more space, coming from more complex forms of matter, like how we theorize here, because that's essentially the interaction that's allowing black holes to exist is quantum gravity, as well as it's dictating gravity itself, is dictating the gravitational constant, it's dictating the expansion of the universe. Because the gravitational waves that are, affect things locally and then outwards, as well as clashing with other gravitational waves from other stars and other things in the universe, it all shapes the universe and it's all relative by that standard. It's just there's two different ways to look at it, and there's multiple areas which quantum gravity exists. So, and put it more simply, if we're going to understand black holes, then that's the last piece that we really need to figure out. Sure, then yeah, but anyway, I'm getting lost in the sauce. But annihilation and Hawking radiation. The virtual particle antiparticle pairs that create Hawking radiation form outside the event horizon, while one particle escapes, its partner falls in with the energy for the escaping particle coming from the black hole's mass. Annihilation within the event horizon is an active area of research, particularly with how it may illuminate black hole shadows. So how we're able to even see black holes in the first place, like that darkness, right? It's kind of it's the contrast basically because of that annihilation and so on. Why a single equation is impossible? I mean, we have the standard model, but ultimately the concepts you combine cannot be unified in a single formula for quantum gravity because the fundamental theories of physics, general relativity, and quantum mechanics break down in the regimes you described. Which this is why this whole video is called Where We're At, because this is where it all breaks. If we can understand where it breaks, then we can understand how to fix it, right? That's typically how you philosophically figure things out. You ask questions, you get answers. So this was the whole idea, at least, of this video, as well as what I've been working on, is asking these questions, trying to figure out where we're at so we can figure out where to go from there. Now, how gravity and the quantum mechanics interact at the most fundamental level, because this is part of what we're trying to figure out. The concepts you highlight illustrate the specific phenomena that a successful theory of quantum gravity must be able to explain. As I didn't even mention quantum gravity in the question to begin with, if you remember. Well, yeah, actually, yeah, I did. But even in the very beginning, when you check out the other video, you'll see the first question here. I don't mention it at all. And it still responds understanding that quantum gravity is necessary in order to make these connections. This is all relative to some way, shape, or form to quantum gravity. So, what replaces the singularity at the center of a black hole? I mean, that's what we kind of have to figure out, is what doesn't exist anymore, what's going on. And what's going on is what's not going on, really. And what's allowed to happen, what's left to be able to happen. And that's where the Bose-Einstein condensate will come into play. Because if we can understand what's happening, or at least the state of the singularity itself, the state of motion and particles as we have analogous ways of making black holes, which I just found out, sonic holes apparently. Black holes that break the sound barrier in a weird way. That is interesting, but that has very similar properties to, a black hole that affects all forms of matter at the photonic scale, basically, at the particle scale. So that's interesting. But how information is preserved during black hole evaporation, a problem known as the black hole information paradox. So that is information preserved? I mean, honestly, I don't think so. If it's breaking down to its most fundamental particles of photons and neutrinos, how the hell are you going to know where it came from? I mean, how are you going to understand the life cycle? How are you going to understand, I mean, the different layers at this point? But I guess if we can understand the different layers of density from the outer shell of the singularity to the inside, right? If we can understand, maybe that's like an exponential function of some sort, perhaps, then maybe we can understand what is in each layer. I mean, kind of, but it's definitely has to be spread equidistant. It's definitely getting stretched spherically because of the rotation is, again, rotation of singularity is going at the speed of light almost. So even if something lands at one point within the singularity, it's instantly being spread out across that entire of following the rotation, I'm assuming, of the sphere itself, of the shape. I mean, all black holes, they're not ellipses, and they're perfect circles. They're perfect spheres. And there's a reason for that, and it's all these different forces that we just listed off. That's maintaining that shape. That's maintaining that point in space for all that stuff to occur. So theoretical physicists are actually working, but at least this is the rundown, this is the summary, at least figuring out where we're at and bringing up all these questions, bringing up all these different concepts because it's all relative to quantum gravity. Check out the longer stream from earlier as well to see where I started, at least with all this, and now where we're going. Lastly, we're going to end off with the whole idea of Bose-Einstein condensate relative to black holes. So BECs serve as analogs, or well, analogies as well. It's very similar in terms of meaning, but analogs for black holes, allowing physicists to create and study black hole-like phenomena in a lab setting, particularly Hawking radiation. In these experiments, BECs is engineered so that its flow becomes supersonic. So this is the whole idea of, sonic event horizon. Not to be confused with Sonic the Hedgehog, but sonic black holes. So using the sound barrier within, I mean, the sound barrier is dictated by the atmosphere as well, because we have an atmosphere. So, I mean, you break the atmosphere with a sonic black hole, basically. It's interesting, but just as light cannot escape a true black hole, a sonic black hole model is crucial for exploring the quantum nature of gravity. Quantum nature of gravity, I mean, yeah, and understanding how these two theoretical frameworks relate to each other. So, as we touched on before, the states of matter seem to work at extremely high levels, extremely high densities and volumes seem to go inversely to how they typically are in our normal 3D space. Just like when, I mean, extreme temperatures, you get solids, like extremely low temperatures when it's super cooled, when things are super cooled, right? Turn to ice, turn hard, and then when they're super hot, they turn into gas. Inversely, and relative to the Bose-Einstein condensate, especially as we observe neutron stars to be super fluids, not gases, right? It goes from, I mean, stars, they're technically big balls of gases, but they're also fluid because they're past a certain temperature threshold, and that's due to, I mean, the amount of nuclear reactions that are occurring within space due to the atoms that exist in that space. It's helium, hydrogen, right? And other things that are all attracted to one another, being attracted through like all our laws of physics that we have now, that we have discovered now, like electromagnetism, uh, nuclear reactions. I mean, the strong nuclear force, the weak force, etc. But obviously, when there's no more, I think what was it, helium, when it runs out of fuel, those atoms don't have a buffer to sustain, the typical star behavior that we see, that we know, and then it ends up into the last stages. Core turns into solid iron, or if it's super dense, depending on how much hydrogen exists in that space that's reacting, etc., etc. It goes past a certain threshold, and then once we get to a neutron star, it's a superfluid at that point, rotating almost at the speed of light as well. But it's still rotating not as fast as a black hole, and that's relative to its magnetic pole, which apparently is I think perpendicular to its rotation in regards to pulsars and neutron stars. So with that understanding, and then understanding that when it's past a certain point of mass, when it's even a neutron star, you get quark clouds, which, I mean, it goes from a fluid to a cloud, and it's like, okay, what the heck? But then once we get to a black hole, then it's like, is a singularity a super solid at that point? Because, I mean, if Bose-Einstein condensates are relative to that, they would be relative to superfluids and supersolids. So that is an interesting topic, and maybe this is where that inverse idea happens. And when we look at Bose-Einstein constant inverse, that idea exists. The inverse cascades into turbulent BECs, where energy from small-scale density waves is transferred to larger scales. So that is very interesting. But I guess this is where we're at so far. This is where I'm at personally in my research. Let me know if this helps you in any way, shape, or form. I mean, there's a lot to read on. There's a lot to learn still, and I don't have that much time to do it. But hopefully, if this serves to help anyone else that is actually interested in the field, if it gets anyone any ideas on how to figure out the relationship, I mean, at some point we will go over all these different forces. We're gonna probably make a list, black hole forces, right? Not to sound like special forces or anything like that, but we'll list all the different forces that are involved in, a black hole event, right? The existence of a black hole. And then what forces do not exist anymore due to things being overwhelmed or overpowered, right? So what's available, what's left, and then we can look at Bose-Einstein condensates and maybe draw some connections there and find some parts of these equations, some parts of these forces that might be coming from quantum gravity itself. It might, honestly, my personal opinion, might be frame dragging. I'm pretty sure it's frame dragging. That's just that whole theory of frame dragging. I'm very sure that is just quantum gravity in a nutshell. It's just the equation for that. I mean, it probably depends on the level that you're looking at, just like how general relativity doesn't work with quantum mechanics, because that is a measuring our observable level of reality that we can see, that we can you know see out in telescopes that aren't electron microscopes. Essentially, you look up at the sky, like, just, I mean, they didn't even have that back then when they figured out Newtonian gravity. So understanding the gravitational constant, maybe relative to it being more like a variable, just like how the cosmological constant itself, underlying quantum gravity, would turn it into a variable. It would just be a very weak variance, which is why, I mean, the constant probably still works in general relativity in this way, but then when you get to extreme levels, it obviously breaks down. So that variance must exist at those extreme levels, more so, obviously, than, yeah, it's probably following an exponential curve of some sort. We just haven't figured out where it is yet. So, or where on that curve it is, where the equations break, where our limits are. And I mean, obviously, the density of a singularity itself, it's not really infinity, because there's not really a zero volume. That's just how that works in that essence. Something is broken, and personally, I think it's the Higgs field, the thing that gives the mass number that is broken, which I mean would explain the fact that it bends space time, and then the frame dragging as well. That's a friction force, and that would explain alongside the fact that something that massive can spin at the speed of light almost. That would explain a lot. And then the forces that are dragging against that friction, the event horizon, the things that are within the event horizon that end up touching the event horizon or that surround it, that's a force that's working against that, which is probably why the singularity doesn't actually reach the speed of light. It just gets close to it, which is maybe where the realistic limits exist. And maybe that's why all these different factors must play into account when it comes to quantum gravity in some way. We just haven't organized it yet. So when I get more time, we'll reorganize it, we'll organize it, and we'll see if anything comes up. I mean, that's the only way to really do it. So, anyways, until next time, this is Spark saying peace. Hopefully, this was informative in some way. It's 30-something minute video, much better than an hour and 30 minutes, I suppose. So, check it out. I know I don't have a lot of art stuff. I don't have even myself. You just have a meter here that you're looking at and a screen. It is what it is. But at the same time, hopefully, you can take the time to read some of these questions. I'm going to probably also take a day to revise this so that it just makes more sense, like language wise, right? It's more correct in its delivery. But after, I mean, working through the misunderstandings that Google was having today with me, especially just check out the longer stream, you'll see instances where Google is just absolutely confused compared to when I was asking literally the same question, this first question, like almost a week ago. Because it seemed to have understood it the first time, and it gave me a lot of good relative information, things that I can look into. And then today, when we tested it, it just did not seem like it understood at all. So whatever the hell's going on with Google or Gemini or whatever, I mean, hopefully it'll figure it out. But we got there. We got there. Maybe it's working too hard in the nuances, or maybe I don't know. But we'll revise this down so it's more sensible and it addresses everything involved, and then we'll test it with other AIs and see what we get. See if we break any of them. That'd be kind of funny. Uh, just all that fun stuff. So, and I don't know, maybe one will have a good estimate because I mean, if I took the time to friggin' do all this, it'd probably take me months to label out every single wave equation and every psi, everything that is involved, all of these forces. And that's some of these don't even, I don't think, have equations yet. Like with the frame dragging, there's no, I don't think there's it's just a theoretical idea. There's no necessarily equation that comes from it yet. I mean, if there was, then maybe that would be quantum gravity. Who knows? But look more into it. You can look more into it as well. I'm sure there's even more to learn about this. If you got more time than me, go ahead and do that. Maybe you'll be the one that figures this all out before I do. But anyways, this is Spark. Until next time, stay curious, ask questions, get answers, and yeah, just be safe out there. I mean, soon we'll figure it out eventually. We'll figure it out. We're getting there. If a 15-year-old can make a connection of Bose-Einstein condensates and superfluids and supersolids to black holes and stuff, I'm sure someone's gonna figure out the rest. So I don't know. There's just so much to think about, and I think that's the individualistic problem when it comes to this. I mean, thank God we had the internet, the collective human consciousness, but any individual person trying to figure all this stuff out with all the nuances included, it's no wonder why it's taking forever to figure it out. No wonder why Einstein couldn't do it in his lifetime, It's a lot. So I'm only in my 30s, and shit, I mean, this is as far as I got so far, and there's still a lot more to go. I don't know, but maybe this will help someone. Anyways, until next time, this is Spark saying peace. Frame dragging.